So we're at a point in the course where we're looking at networks and services. And in the last lecture, we looked at some of the services that made buildings work better in more healthy ways and how they linked buildings into larger systems, electrical systems, sewer systems, freshwater systems. In this lecture, I want to look at another set of networks and another set of inventions that have to do more with how buildings connect with one another, how cities grow, et cetera, and how the technology that gets us sort of between built works also impacted the way that we constructed, the way we built. The internal combustion engine, alongside things like the electric light and freshwater technologies, is one of the major differences between the sort of pre-20th century era and the world we live in today. And to Robert Gordon's point in his book, The Rise and Fall of American Growth, internal combustion engine is one of the things that leads to this incredible burst of gross domestic product, if not, like sanitation and electricity, also leading to salutary effects on our health, right? In some ways, the internal combustion engine is exactly the opposite. Nonetheless, though, it's a really important technology that changes the way we do business and that changes the way our cities in particular work. So I want to look in this lecture at some of the ways that building responds to the internal combustion engine and is changed by it. When we talk about internal combustion, we're talking about a series of technologies that basically combine the energy source with the power cycle. So in a steam engine, the energy source is outside, it's external to the power cycle itself. Internal combustion offers greater efficiencies by making a more direct connection between burning of fuel and obtaining power. There's a long history of attempts to do this, not, of course, with steam, because water and fire don't mix so much, but with various types of fuel that actually moves the pieces of an engine itself. This goes back to the 1790s or so in Great Britain, and throughout the early 19th century, there are efforts to try to create better and better engines, better and better power sources. In the 1860s and 1870s, a series of experiments in Germany, particularly by Otto, Daimler, and Maybach, start to produce workable internal combustion engines that can be mounted to smaller and smaller vehicles. So there have been efforts to put steam engines onto what had formerly been horse carts. Those are ungainly. They require an awful lot of effort to tend the fire. The internal combustion engine seems to offer a better way to do this, that it can be self-contained. The driver doesn't have to worry about stoking the fire. And by 1880, Carl Benz has produced vehicles like the replica that you see here, a commercially viable three-wheeled cart in this case that has a small internal combustion motor on the back that drives the wheels and allows it to move. There are other internal combustion technologies, some of which we'll look at a little bit later. Rocketry is internal combustion. Goddard in the United States pioneers that in 1926. And aircraft, both first internal combustion piston engine aircraft, but by 1939 the first jets are being used or being experimented with in Germany. So the first thing I want to look at is how building responds to the popularity of internal combustion. Benz and later Daimler and Maybach, and then eventually Studebaker and Ford in the United States pioneer the commercial production of automobiles with internal combustion engines attached. They're complicated machines. They require a good deal of standardization and a good deal of assembly. And one of the first ways that architecture or building responds to this new technology is by providing buildings that actually allow for the manufacture of these machines, of the engines and of the cars. The gentleman that you see on the left in this picture is Albert Kahn, a Detroit architect, emigre architect, who partnered with Henry Ford, who you see here standing next to him, in the production of factory buildings that allowed for the production of automobiles. And there's a kind of one-to-one link between some of the building technologies that we've looked at and some of the automotive the technologies results that are coming off of the assembly line. Kahn took a very standardized, what we would call a very tailorized approach. He was a big believer in scientific management. And among his other achievements was the way that his office was structured, very much like offices would be throughout the 20th century. Kahn was a very early pioneer in this kind of brigade system of office hierarchy, so that each complex project would get broken out into structural, mechanical, architectural, and what he called design. Those would all report to a series of heads who would then report to administrators within the firm. And you can see that there's a whole other division that has to do with both running the office, but also coordinating construction. Kahn and his brother Julius Kahn were not only architects, there was also engineering within the firm, but they were also inventors. And Julius in particular pioneered a type of reinforcing bar, and we've seen lots of patents so far for reinforcing bars. This is the so-called Kahn bar on the upper left. And they develop a company that Julius runs. It ends up becoming independent of the architecture firm called Kahn. They produce the materials that go into a lot of the factory buildings, especially that the Albert Kahn firm designs. You can see that the Kahn bar is a way of kind of combining shear reinforcement with tensile reinforcement. So Kahn sells it as a kind of way to turn a reinforced concrete slab or beam into a truss with some of the same efficiencies. But Kahn does other things as well. They pioneer the use of lightweight metal arches to provide for what we recognize as jack arch construction, but this time out of concrete instead of brick. So some of the early pure concrete floors following on from the experiments that Ransom does. You can see one of those on the lower left. And they also take ideas from Onnebeek, from Ransom, and really turn their design expertise and their engineering expertise into a system. So on the right, you see an advertisement for the Kahn system of factory construction that's being advertised in Great Britain. If you look at the address, this is a sort of franchise approach, very similar to Onnebeek's. So you have the design expertise, engineering expertise, construction expertise, but you also have patented systems that are licensed for the kind of construction that the Kahn brothers are able to provide for their clients. Kahn did not suffer fools, and in addition to all of this invention, the principles of scientific management also led to a sort of culture of what today we might call integrated design, where, as you can see from the quote, Kahn didn't believe in the kind of genius architect myth. If you went to work for his firm, you were there to be part of a team and to play your role in getting the job done. Little encouragement to the temperamental in our men, and this lessens our problems. You can imagine the sort of culture of the firm. But this, I think, idea also translated into the architecture, that the architecture of the factories that Kahn's firm did always took a back seat to the logic of the production. Kahn's firm did lots of much fancier buildings, museums throughout Detroit, office buildings in Detroit, and many buildings on the campus of the University of Michigan. They were all very competent, very well done Beaux-Arts buildings. But his factory buildings really were kind of machine-oriented. And you can see from this early work for the Packard car company in Detroit that it borrows a lot from Ransom's early factory construction. A concrete frame infilled with just enough sill to keep people from falling out, very, very large windows to bring in as much daylight as possible, standard modules so that as machinery is being put in, it can be moved around relatively easily, and a system of construction using his brother Julius's techniques and patents that allowed for skinnier slabs, thinner beams, thinner columns, and more efficient construction. The Kahn firms, Albert Kahn and Associates, and then Truss Kahn, get a reputation in the industry for being the kind of industry architects for manufacturing buildings, mostly for automobiles. Here is one in Buffalo where you can see that they're using concrete to get north-looking skylights, so a vast factory floor can be very easily illuminated with north light without bringing in any direct glare or sunlight. And you get some sense for what is clearly a kind of pre-electric factory in many ways. You can see all of the shafts and the belts that are turning the tools that people are using. Over time, of course, those open rotating shafts and belts, which are very dangerous, get replaced by electricity that again brings the kind of motive power directly to the workstation. This is a sort of early factory floor. It's not quite what we would call an assembly line yet. And that really comes with the Ford Company's Highland Park plant, which is built just outside Detroit in 1909. And this is really a collaboration between Henry Ford, who has this vision of the standardized automobile, the result of hundreds and hundreds of repetitive tasks with elements that are exactly the same. There's no kind of handicraft here. There's no sort of artisanal work. These are not stagecoaches or carriages. These are mass-produced machines. And Ford's vision is for a factory where he can put people to work, each of them doing the same task over and over and over again. Relatively unskilled labor, right? Breaking a complicated task down into hundreds of little, not very complicated jobs. Kahn's response is a concrete frame building, very much like his early work for Packard and for Pierce. You can see, again, gigantic windows to bring in as much daylight, and if you look at the slide on the right, as much fresh air as possible. And he also develops an idea about gravity-fed production. So all of the hundreds of pieces that go into a Model T get taken up to the top floor. And as the automobile gets assembled, you get heavier and heavier pieces that they're able to drive down to the various floors. So the assembly line wraps back and forth, starting on the fourth floor and working its way down, as you can see on the right, to the ground floor. There's a kind of idea here about the architecture and the automobiles being similar in some ways, that it's almost a factory production that creates the concrete columns, the concrete slabs, and that in turn, the standardization and all that in turn allows for the very efficient organization of an assembly line down below. Ford we think of as kind of famous or notorious for just turning everything into the most efficient task possible. The only color that you can get a Model T in is black, because black paint was not only easy to obtain, but it dried faster than any other color Ford could find. And so that saved time on the assembly line. It allowed them to turn out these cars over and over and over again. And here you get a sense for the scale of the production. Brand new cars lined up outside the factory. Around World War I, the gravity-fed practice that Kahn and Ford pioneered at Highland Park changes to a horizontal layout. With electric power, it's easier to move heavier pieces around. So you get overhead electric cranes and electrically run conveyor links that allow for a more spread out horizontal approach. Concrete gets better, high-strength steel gets better. And this enables longer spans, which allows for larger machinery. The columns don't get in the way so much. Electrical lighting and structural advances that bring in, as you saw, some roof monitors, mean that the machinery can be positioned according to whatever the organization has to be. They don't have to be near windows if they require a lot of fine vision tasks. They can be put anywhere on the factory floor. Materials get moved around by crane, by electric conveyor, instead of by hand, which speeds things up and requires fewer people. And because electricity can be taken anywhere to the factory floor, the machinery doesn't have to be lined up along these rotating mechanical shafts and belts. the production line can develop exactly in lockstep with the sequence. Kahn's work for the automotive industry follows suit, and you start to see more articulated, more kind of efficient, or more dedicated structures that respond better to the way that these assembly lines are developing. This building for a forge, a very hot process in Detroit for Packard, shows that Kahn is able to use steel to produce shapes with a lot of natural ventilation that are going to take the extra heat from the forges and just discharge them through these upper story windows. The section of this also brings in a ton of natural daylight at all levels and allows for the very kind of fine-grained opening and closing of windows to make sure that there's enough air moving through to keep the space, if not comfortable, at least relatively cool. The greatest example of Kahn and Ford working together to produce the buildings that are going to produce internal combustion automobiles is the complex at River Rouge, just south of Detroit, that would become Ford's main production plant by the 1930s. You get a sense for the scale here with the kind of overall site on the left. You can see that there are, in the upper left, there are the generating buildings. The smokestacks are the area where the generators are that use coal to produce power in the form of electricity. There's a slip off of the Detroit's main river, and there are rail links both to the south and east and also to the west. And the idea is that all of the raw materials come in from the river, from the rail links on the eastern side, and everything sort of tracks through. You get things getting put together in these various buildings, and at the end, on the west side, you get finished cars. So you can compare this in scale to the Highland Park plant, and clearly the automobile has gotten much more popular and the market has gotten much bigger, but the process has also gotten more elaborate, more spread out thanks to electricity. You see an electric overhead crane there in the shot on the right, and also more effective because the factory floor can be laid out horizontally. And as you can see, there is light coming in both from upper monitors that use high-strength steel to achieve these big spans, but also from electric lighting. Nowhere, I think, is the kind of parallel between scientific management in building construction and scientific management on the assembly line clearer than at River Rouge. This is a sort of advertising document that the Ford company produced that shows sort of how the entire complex works as one giant machine. And you can see that raw materials are coming in from the slip. There's a lumber boat, there's an iron ore boat. There are blast furnaces that are located next to the powerhouse. Both of those use coal to produce their heat. The raw ore gets turned into steel and iron in the foundries and furnaces on the kind of upper right. And gradually things get more and more refined as they go down to the lower left. And you see all of the arrows sort of show you the flow chart for how this system works. If you zoom in, you can see that the buildings themselves are kind of aligned in ways that reflect the flow of materials through River Rouge. So all of these shed roofs, all of these very long linear structures, and all of these kind of spread out horizontal structures are designed to assist in the process, right? It's like one giant machine, or you could think of it maybe in today's terms as one giant kind of silicon chip design, where all of the materials are flowing through these buildings that Kahn has designed in the most efficient way possible. You can also get a sense for the standardization that as technology gets better or as they need to replace machines, it's very easy to do because the buildings are all sort of standardized. The structural spans are the same in each building so that you can move pieces around relatively easily. Over time, Kahn's work for Ford gets kind of more structurally sophisticated, and his work for other companies starts to show that they're clearly learning what the materials they're using are capable of. So high-strength steel in the form of trusses goes for more and more efficient structures. Here, the half-ton truck plant that the Ford firm does in 1937 uses riveted and welded connections to achieve these monitors that bring daylight again into the center of the space. And you can get a sense here for the efficiency that steel brings to the process, right? That it is much finer. The columns are much thinner than the concrete that Ford had been using in the early part of the 20th century. We'll talk about aircraft toward the end of the lecture, but I did want to show that Ford also worked for other companies that made other types of internal combustion vehicles. And perhaps is best known, although in a slightly roundabout way, is this factory outside Baltimore for the Martin Company, which the process starts in 1929 with the low-rise building that you see in front. On the eve of World War II, Martin builds these two other very large factory buildings that help them assemble the flying boats that the government's going to use to prosecute the war. You can see on the right, this drawing from Kahn's office shows again that steel is being used to bring daylight into the center of this vast open floor. And here you get a sense for both the scale of the operation, right? The planes, of course, are much larger than cars. The wingspans require a lot more space to maneuver the finished products around. And sort of everything that we've talked about in the last few lectures is here. The long span steel trusses, which enable open, clear span spaces of 100 or 200 feet beneath them. You can see that there are cables and conduits strung throughout the ceiling that are taking electric power to overhead cranes, to machinery that's on the floor. You can see that there's electric light, and the electric lights are working in conjunction with the monitors, the little or the linear skylights. Those not only bring in daylight, but they also allow air to be exhausted off the floor. And this is not only an efficient factory, it was also in the 20s and 30s one of many factories that inspired architects to think about what the possibility of a kind of new architectural language, right, a new industrial language was like. The sort of romance of architecture as a machine was captured by a lot of designers. Corbusier, of course, most famously said that the house is a machine for living in. But his contemporaries also looked at examples like this and found inspiration. When Mies van der Rohe is entering a competition for a concert hall, he sees the Martin Company plant as a kind of ready-made. And his entry for that competition literally takes the background of the Martin plant, collages over the plane, although you can see that they are actually still in the background of his collage. And he basically says that this is a way of creating universal space, and it's architecturally acceptable, right? All we have to do is hang a ceiling, a couple of walls, put in a sculpture to indicate that this is some sort of cultural facility. And we can use the kind of ready-made industrial architecture that firms like Albert Kahn are producing as an inspiration for the cultural buildings that are going to come in the 20th century. All right, whether you quite buy into that or not, the war effort for World War II really jumpstarts factory construction. And Kahn's firm is one of the leading firms to produce the buildings that now are not going to produce cars, but they're going to produce the kind of materiel for the American forces in World War II. So here in 1941, as the world is sort of heading to war, Kahn's commissioned to design a manufacturing plant at a small airport outside Detroit. And this is a building to produce bombers. And Kahn's factory has to use these very, very large spans to accommodate even larger wingspans on the planes that they're building. And you see those on the right-hand side. It's not just the building, though. The Willow Run plant and a number of other large wartime factories rely on these principles of scientific management. So part of the Willow Run plant is a design office that's attached directly to the factory floor. And there's a staff of a couple hundred engineers, draftsmen, who are working on the design of the aircraft. So even as the planes are coming off of the assembly line, there's a team of designers that are looking for ways to build them quicker, more effectively. They're taking on board suggestions or ideas as the planes are moving through the factory floor. And that's really only possible with this kind of iterative process, the assembly line that produces the same thing over and over and over again. These engineers here are learning from the process. Because the design office is connected directly to the factory floor, they're able to both hear from the factory floor when things could be going better, and they're able to try things out directly. And I love the shot of the engineers kind of lying on the tables, drawing on these giant sheets of vellum as the planes are coming off the line next door. In the next part of the lecture, we'll look at not architecture that goes in or that's influenced by internal combustion in the automobile. We'll look at engineering and construction that supports the automobile by providing the network of roads that countries need to make the most use of them, both economically, but also in terms of leisure travel or commuting. Road and bridge construction is probably one of the greatest stories of 20th century building, and we'll take a look at how the automobile both inspires it and also provides kind of new challenges for builders in the early to mid 20th century.